Hello everyone, welcome to our presentation of ROBOTune, High Dimensional Configuration Tuning for Cluster-Based Data Analytics. I am Muhib Khan. I am a PhD student at Florida State University and this is a paper with my professor, Dr. Wei-Kwan Yu. So, this is the outline of our presentation. We are first going to introduce ROBOTune, then go over the background and motivation of the paper, then the design of ROBOTune, then some implementation details, some evaluation, and conclude at the end. So what is ROBOTune? ROBOTune is an automatic configuration tuning framework. What does it aim to tune? ROBOTune aims to tune cluster-based data analytics applications. Specifically, ROBOTune is geared towards tuning configuration parameters of Apache Spark. So now we go over the background and motivation of ROBOTune. What is the need for tuning Spark? Most data analytics workloads are recurring jobs in a cluster. Thus, optimization can save a tremendous amount of time and resources. One can ask, why not use the default configuration? Because it underperforms significantly compared to near-optimal configurations, it is suboptimal to do so. Why not tune manually? Random trial and error by inexperienced users would give vastly different results. And this is because of the complex relationship between the configuration and performance. So what are the challenges for automatically tuning parameters of Apache Spark? The first challenge is the high dimensionality of the configuration space. The number of Spark configuration parameter has increased by 10 times since its initial release. An addition of each configuration parameter exponentially increases the complexity of the configuration space. The second challenge is costly sample collection. Sample collection of Spark workloads is a costly proposition, and state-of-the-art learning-based tuners require a significant number of samples to work, at least 2,000, which is impractical in most real-life scenarios. In order to be feasible, auto-tuners should be cost-efficient and flexible. Now we give a bit of background on Bayesian optimization, which is an important component of our paper. Bayesian optimization is a powerful method of optimizing expensive black box functions. It works for non-convex and noisy functions. It effectively avoids local optima. Also, a minimal number of samples is required for tuning and search. Thus, it is very cost efficient. There is one caveat though. It works best when the number of dimensions is low. Now we go over the design of ROBOTune. In this slide, we can see the design overview of ROBOTune. From here, we see there are three main components: parameter selection, memory sampling, and Bayesian optimization. Now, we give a design overview of the three components. Memory sampling consists of latent hypercube sampling with a parameter selection cache and a configuration memorization buffer. We would give more details on this in a later slide. Parameter selection module selects impactful parameters using a random forest model. And Bayesian optimization engine balances exploration and exploitation during the tuning. It iteratively searches for the best configuration using a Gaussian process model and a portfolio of acquisition functions. In the memory sampling module, we choose to use latent hypercube sampling. This is because Latin hypercube sampling requires fewer samples than random sampling to reach a similar conclusion. We also introduced a concept called parameter selection cache. This stems from the observation that the high-impact parameters of a workload remain the same for a range of datasets. We can thus reuse these selected parameters for new datasets of the same workload. This can significantly reduce the tuning cost of a workload. We also introduced configuration memorization buffer, which includes well-performing configurations from previous tuning sessions in the BO training set. This can significantly speed up the search process for optimal configurations. For parameter selection, we can use ML models to identify the impactful parameters. This can be done by measuring the strength of the relationship between the objective and the parameters. In our experiments, we see the tree-based estimators such as random forest perform better with lower number of samples than linear models. Such an example can be seen in the graph where we plot the R-squared score of different models for 3 different datasets of the PageRank workloads. We also note that we do not need a perfect predictor for identifying the impactful parameters. For feature ranking or parameter ranking with random forest, we choose to use a method named mean decrease in accuracy or MDA. This is a method that is slower but more robust than the default method. We also handle collinearity in the parameter space by grouping dependent parameters with the independent one during the parameter importance calculation. We now give details on the Bayesian optimization engine. Bayesian optimization engine is composed of two main components: a Bayesian statistical model for modeling the objective function, which is also known as the surrogate, and secondly, an acquisition function that guides the search by selecting candidate points for sampling. The surrogate can be random forest, gradient boosted trees, Gaussian process, etc. For ROBOTune, we choose to use Gaussian process. Gaussian process is a distribution over multivariate functions. It provides a theoretically justified way to trade off exploration and exploitation. It also has been applied successfully to real-world systems. For choice of acquisition functions, there are main three options: probability of improvement, expected improvement, and lower confidence bound. However, no acquisition function is guaranteed to perform the best on an unknown objective, which is what we have at our hand with different Spark workloads and datasets. So we ask, why not use all of them? Hence, we choose GPH, which is a portfolio of acquisition functions. In GPH, the probability of choosing an acquisition function is updated based on the cumulative rewards at each step. Now we give some implementation details. Parameter selection is implemented using the scikit-learn library. Memory sampling is implemented using the DoPy library, also the scikit-learn library. Bayesian optimization engine is built on top of the scikit-optimize library. More details can be found in the paper. Now we go over the evaluation of our paper. In our experimental setup, we use 6 nodes with a total of 192 cores and 1152 GB of memory. We use Spark 2.4.1 and HDFS 2.7.3. We tune 44 core performance related parameters that cover shuffle, networking, memory management, execution behavior, etc. An exhaustive search of this configuration space is infeasible due to the enormity and high dimensionality of the configuration space. The comparative solutions and workloads in our evaluation are BaseConfig, which is a search-based tuning approach that uses a divide and diverge sampling and recursive bound and search algorithm. Ganthar, which is a configuration tuner for Hadoop, which utilizes genetic algorithm for searching near optimal configurations. As a baseline, we use random search, which is a simple random search-based tuning approach. We use 5 representative workloads, each with 3 datasets from the Spark benchmark. These are PageRank, K-means, connected components, logistic regression, and TerraSort. We first compare the different optimal configurations found by the 3 tuners. ROBOTune outperforms BaseConfig by 1.14 times on average and up to 1.3 times. Similarly, it outperforms Ganthar by 1.15 times on average and up to 1.28 times. We can see similar result for random search. We can see that ROBOTune finds much better configuration for PageRank and connected components and moderately better for TerraSort. In terms of search cost, the overall improvement of ROBOTune over BaseConfig is 1.59 times on average and up to 2.27 times. The improvement over Ganthar is 1.53 times on average and up to 1.71 times. Random search, on the other hand, is outperformed by 1.6 times on average and up to 1.93 times. So why is the search cost lower for ROBOTune? The distribution of workload execution time shows that ROBOTune in general samples better performing configurations. We can see from 2 example graphs that the median of execution time for ROBOTune is much lower than the comparative solutions. ROBOTune avoids underperforming and imbalanced configuration regions and in turn lowers search cost. We also compare the search speed of ROBOTune with other tuners. For an example, we include two graphs of the PageRank dataset 1 and PageRank dataset 3 and the search speed of different tuners in this slide. In general, ROBOTune quickly finds configurations within 5% of the observed best. Also, using well-performing samples in the initial set, ROBOTune immediately gets within 10% of the best observed time and then further improves the performance, which can be seen in the PageRank dataset 3 graph. Now we conclude at the end. In conclusion, we have designed and developed ROBOTune for tuning configurations of data analytics frameworks while tackling the issues of high dimensionality of the configuration space and complex configuration performance relationship. Our evaluation shows that ROBOTune achieves a significant search cost and search speed improvement while finding better or similar configurations. The sponsor of this research was NSF. Any questions?